Hopefully I would be live. Hopefully I would be live. Hopefully I would be live. I don't know if. Okay, I'm live. Okay, I'm live. So I closed the tab because now I think that I'm live. And now we'll be studying or working with our C program. Syntax and semantic errors. Software errors are prevalent. It is easy to make them and it is hard to find them. In this chapter, we'll explore topics related to finding and removal of bugs within our C++ programs, including learning how to use integrated debugger, that is the part of our IDE. Although tools, although debugging tools and techniques are part of C++ standard, learning to find and remove bugs in the programs you write is an extremely important part of being a successful programmer. Therefore, we'll spend a bit of time covering such topics, such that as the programs you write become more complex, your ability to diagnose and remedy issue advances at similar pace. If you have experienced debugging programs in another programming language, much of this will be familiar to you. Programming can be challenging. C++ is somewhat a quirky language. Put those two together and there are a lot of ways to make mistakes. Errors generally fall into one of two categories: syntax errors, semantic errors, logic errors. A syntax error occurs when you write a statement that is not valid according to the grammar of C++ language. This includes errors such as missing semicolons, mismatched parentheses. I hope now my voice becomes much more clear. My mic was covered with something else, something I cannot tell you. Write statements that is not valid according to the grammar C++ language. This includes errors such as missing semicolons, mismatched parentheses or braces, etc. For example, the following program contains quite few syntax errors. Okay, one of the closing brace is missing. Int 1x variable name cannot start with a number, that is for sure. Standard cout, hi there. No semicolon should have been over there. Extraneous x++ is also not valid. Semicolon operator plus plus does not exist. Missing semicolon. Unfortunately, the compiler will detect a syntax error and issue a compilation warning or error. So you usually identify and fix the problem. It's just the matter of compiling again until you get rid of this errors. Semantic errors is an error in meaning. These occur when a statement is syntactically valid but either violates other rules of language or does not know what the programmer intended. Some kind of semantic error can be caught by the compiler. Common examples include using undeclared variable type mismatches when we use an object of wrong type somewhere. For example, the following program contains several compile time semantic errors. Int main 5 equal to x, x not declared, cannot assign a value to 5. X is not declared and so you cannot, okay, return hello. Hello cannot be converted to an int. Int type mismatch. Other semantic errors only manifest at runtime. Sometimes these can cause the program to crash, such as in this case, of division by 0. Int main a equal to 10, b equal to b, standard cout, standard console out a, okay, divide by b equal to a actually divided by b. Division by 0 is underdefined and most often this will produce Wrong value or behavior. No initializer provided. Okay. Use of uninitialized leads to the undefined result. Can we just test some of these? Fortunately, I've written some code, and now let's start. Int a, we are using list initialization over here. B, sorry, 0. Standard cout a divided by b, and simply a new line. G++ main.cpp -o main floating point expectation core dumped. What kind of error is this? I don't know. Let's go back to the program and try and execute this different program. X has been declared but not initialized with some value. Standard cout, I am hoping that it prints 0, because by default this doesn't hold any value, so it should return 0. G++ main. Oh, it is giving me some random value, which main.cpp. Or so this is the function declaration, return x minus y, but it doesn't due to the wrong operator being used. Int add function is supposed to perform addition. Wait, the f. Okay, so int main function 5 plus 3 add 5 3 should produce 8 but produces 2. Yeah, that is because the programmer did not include the correct operator. Int main function returns here standard cout, so this never executes. The above but in most non-trivial program, runtime semantic error are not easy to find by eyeballing the code. This is where debugging techniques come in handy. Next lesson, debugging process. Let's say you have written a program, it is not working correctly. The code compiles fine, but when you run it, you are getting an incorrect result. You must have semantic error somewhere. How can you find it? If you have been following best practices of writing little bit of code and testing it, you may have a good idea where your error is, or you may have no clue at all. All bugs stem from simple premise. Something that you thought was correct isn't. Actually figuring out where that error is can be challenging. In this lesson, we'll outline general process of debugging a program. Because we haven't covered that many C++ topics yet, our example program in this chapter are going to be pretty basic. That may make some of the techniques we are showing here seem excessive. However, keep in mind that these techniques are designed to be used with larger, more complex programs, and will be of more use in such setting where you need them the most. General approach to debugging. Once a problem has been identified, debugging the problem generally consists of 6 steps. Finding the root cause of the problem, using the line of code that's not working. We'll discuss some of the strategies how to do this in next lesson. Ensure you understand why the issue is occurring. Determine how you will fix the issue. Repair the issue causing the problem. Retest to ensure the problem has been fixed. Retest to ensure no new problems have emerged. Let us use a real life analogy here. Let's say one evening you go to some ice, you go to get some ice from the ice dispenser in your freezer. You put your cup up to the dispenser, press the lever, and nothing comes out. Oh, 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 you discovered some kind of defect. What would you do? You would generally start investigation to see if you could identify the root cause of the issue. Find the root cause. Since you hear the ice dispenser trying to deliver ice, it's probably not the ice delivery mechanism itself. So you can open the freezer, examine the ice tray, no ice. Is that the root cause of the issue? No, it's another symptom. After further examination, you determine that the ice maker does not appear to be making ice. Is the problem ice maker or something else? The freezer is still cold, the water line isn't clogged, everything else seems to be working, so you conclude that the root cause is the ice maker is non-functional. Understand the problem. This is the simple case. A broken ice maker won't make ice. Determine a fix. At this point, you have several options to fix. You could work around the issue, buy bags of ice from the store. You could try to diagnose the ice maker further to see if there's a part that can be repaired. You could buy a new ice maker, install it in place of the current one. Now you could buy a new freezer and you decide to buy a new ice maker. Repair the issue. Once the ice maker has arrived, you install it. Retest. After turning the electricity back on and waiting overnight, your new ice maker starts making ice. No issues are discovered. Now let's apply this process to our simple program from the previous lesson. Int add, int x, int y. Okay, cool. This code is nice in one regard. Bug is very apparent because the wrong answer get printed to the screen via line 10. That gives us the starting point of our investigation. Find the root cause. In the line 10 we can see that we are passing in the literal for argument 5 and 3. So there is no room of error there. Since the input to the function add are correct but the output isn't, it's pretty apparent that the function add must be producing wrong value. Only statement in function add is the return statement, which must be the culprit. We found the prob we have found the problem line. Now that we know that where to focus our attention, noticing that we are subtracting instead of adding is something you are likely to find via inspection. Understand the problem. In this case, it is obvious why wrong value is being generated. We are using the wrong operator. Determine the fix. Will simply change the operator minus to the operator plus. Repair the issue. This is actually changing the operator minus, ensuring the program recompile retest after implementing. Rerunning the program will indicate that our program now produces the correct value of it. For this simple program, that's all the testing that's needed. This example is trivial but illustrates the basic process you will go through when diagnosing a program. Strategy for debugging. When debugging a program, in most cases, the vast majority of the time will be spent to finding where the error actually is. Once the issue is found, remaining steps, fixing the issue and validating that the issue was fixed, are often trivial in comparison. In this lesson, we will start exploring how to find errors. Let's say you have noticed a program and want to track the cause of that specific problem down. In many cases, especially in smaller programs, we can approximate where the issue is likely to be based on the nature of error. Way and the way the program is structured. Consider the following program snippet. sort them in alphabetical, print them in sorted list. If you expect this program to print names in alphabetical order but it printed them in opposite order, the program is probably in sort names function. In cases where you can narrow the problem down to a specific function, you may be able to spot the issue just by looking at the code. Let me use some eye drops. And to get more complex, finding issue by code inspection become more complex as first there is a lot more code to look at. Looking at every line of code in the program that is thousands of lines can take a very long time, not to mention it's incredibly boring. Second, the code itself tends to be more complex with more possible places of things to go wrong. Second, the code's behavior may not give you many clues as to where things are going wrong. If you wrote a program to output stock recommendation and it actually output nothing at all, you probably wouldn't have much of the lead on where to start looking for problems. Finally, bugs can be caused by making bad assumptions. It's almost impossible to visually spot a bug caused by bad assumption because you're likely to make some bad assumption when inspecting the code and not notice the error. So if we have an issue that we can't find via code inspection, how do we find it? Finding problems by running the program. Fortunately, if we can't find the issue at code inspection, then there is another avenue we can take. We can watch the behavior of the program as it runs and try to diagnose the issue from that. This approach can be generalized as figure out how to produce the problem, run the program and gather information to narrow down where the problem is, repeat the prior step until you find the problem. For the rest of this chapter, we'll discuss technique to facilitate this approach. First and the most important step in finding a problem is to be able to reproduce the problem. Reproducing the problem means making the problem appear in a consistent manner. The reason is simple, it is extremely hard to find issue unless you can observe it occurring. Back to the ice dispenser analogy. Let's say one day your friends tell you that the ice dispenser isn't working, you go to look at it, it works fine. How would you diagnose the problem? It would be very difficult. However, if you could actually see the issue of the ice dispenser not working, then you could start to diagnose why it wasn't working much more effectively. If a software issue is blatant, the program crashes in same place every time you run it, then reproducing the problem can be trivial. However, sometimes reproducing an issue can be a lot more difficult. Problem may only occur in certain computers or in particular circumstances. Example, when the user enters certain input. In such cases, generating a set of reproduction steps can be useful. Reproduction steps are a list of clear and precise steps that can be followed to cause an issue to reoccur with high level of predictability. The goal is to be able to cause the issue to reoccur as much as possible. So if we run our program over and over and look for clues to determine what's causing the problem, if the issue can be reproduced 100% of the time, that's ideal. But less than 100% reproducibility can be okay. An issue that only occurs 50% of the time simply means that it will take twice as long to diagnose the issue. As long as the half the time of program won't exhibit the problem does not contribute any useful diagnostic information. Once you can reasonably reproduce the problem, the next step is to figure out where's the code. Based on the nature of problem, this may be easy or difficult. For the sake of it, let's say we don't have much of an idea where the problem actually is. How do we find it? The analogy will serve us well here. Let's play a game high-low. I'm going to ask you to guess a number between 1 to 10. For each guess you make, I'll tell you whether the guess is too high or too low. An instance of this game might look like you 5 too low, too high, too low, 7 correct. In above game, you don't have to guess every number to find the number I was thinking of. Through the process of making guesses and considering the information you can learn from each guess, you can home in on the correct number. Only a few guesses. If you use optimal strategy, you can always find the number I'm thinking of in 4 or few guesses. You can use similar process to debug the program. In the worst case, you have no idea where the bug is. However, we do know the problem must be in somewhere in the code that executes between the beginning and the point where the program exhibits the first incorrect symptom that we can observe, that at least rules out the parts of the program that execute at first observable symptom, but still potentially leaves a lot of code to cover. To diagnose the issue, we'll make some educated guesses about the problem and the goal of homing in our problem quickly. Often, whatever it was that caused us to notice the problem will give us an initial guess that's close to where the actual problem is. For example, if the problem isn't writing data to a file when it should be, then the issue is probably somewhere in the code that handles the writing to a file. Duh. If the problem is in writing the data to a file when it should be, the issue is somewhere in the code that handles writing. Then we can use the high-low strategy to try and isolate the problem, what the problem actually is. Well, if at some point in our program we can prove the problem has not occurred yet, this analogous is to receiving too low, high-low result. We know the problem must be somewhere later in the program. For example, if our program is crashing in the same place every time, we can prove that program has not crashed at particular point then the crash must be later in the code. If at some point in a program we can observe incorrect behavior related to the problem, then the too high, high, low. The program must be somewhere earlier in the program. Problem must be somewhere earlier. For example, let's say a program prints value of some variable. You were expecting it to print value 2, but it printed 8 instead. Variable x must have wrong value. If at some point during the execution of our program we can see that variable x already has value 8, then we know the problem must have occurred before that point. ILO analysis is perfect, we can also sometimes remove the entire sections of a code from consideration without gaining any information whether the actual problem is before or after that point. We'll show examples of three cases in the next lesson. Eventually, with enough guesses and some good technique, we can home in on the exact line causing the problem. If we have made any bad assumption, this will help us discover where. When you have excluded everything else, the only thing left must be causing the problem. Then it must be the matter of understanding why. What guessing strategy you want to use is up to you. Best one depends on the type of bug it is. So you are likely want to try many different approaches to narrow down the issue. As you gain experience in debugging issue, your intuition will help guide you. So how do we make guesses? There are many ways to do so. We are going to start with some simple approaches in next chapter, and then we will build on this and explore others in future chapters. Basic debugging tactics. In previous lesson, we explored a strategy of finding issue by running our programs and using guesswork to home in on where the problem is. In this lesson, we'll explore some basic tactics for actually making those guesses and collective commenting out your code. Let's start with an easy one. If your program is exhibiting erroneous behavior, one way to reduce the amount of code you have to search through is to comment out some code and see if the issue persists. If issue remains unchanged, the commented out code probably wasn't responsible. Consider the following code. Let's say this program is supposed to print the names of user enters in alphabetical order, but it is printing them in reverse alphabetical order. What's the problem? Is get names entering names incorrectly? Is sort names sorting them backwards? Is print names printing them backward? It could be any of those things. But we might suspect do maintenance has nothing to do with the problem, so let's comment it out. If the problem goes away, then do maintenance must be causing the problem, and we should focus our attention there. If the problem is unchanged, which is more likely, then we can reasonably assume that do maintenance wasn't at fault, and we can exclude that entire function from our search for now. This doesn't help us understand whether the actual problem is before or after the call to do maintenance, but it does reduces the amount of code we have to subsequently look through. If commenting out do maintenance causes the problem to morph into some other related program stops printing names, then it is likely that do maintenance is doing something useful that some other code is dependent on. In this case, we probably can't tell whether the issue is in do maintenance or elsewhere, so we can uncomment do maintenance and try some other approach. Do not forget which functions you have commented so that you can uncomment them later. After making many debugging related changes, it is very easy to miss out on doing one or two. If that happens, you'll end up fixing one bug but introducing others. Having a good version control system is extremely useful, so you can diff your code against the main branch to see all the debugging related differentiate changes you have made to ensure that they are reverted before you commit your changes. An alternate approach to repeatedly adding or removing and uncommenting debugging is to use third-party library that will let you leave debug statements in your code but compile them out in the release mode via precursor macro. DBG is one such header library that exists to help you facilitate this via macro precursor macro. We'll discuss about header only libraries in lesson inline functions and variables. Another problem common in more complex programming is that program is calling a function too many or too few times. In such cases, it can be helpful to place statements at top of your functions to print function name. Also, it can be useful to place you can see which program is getting called. Tip when printing information for debugging, use standard CR instead of standard cout. One reason is for that some may be buffered, which means a bit of time may pass between you when you ask standard cout to output text and what it actually does. If your output is using cout, then your program crashes immediately afterward. Standard cout may or may not have actual output yet. This can mislead you about where the issue is. On the other hand, standard CER is unbuffered, which means anything you send it to output immediately. This will help you ensure all debugging output appears as soon as possible at cost of some performance, which you usually don't care about when debugging. Using standard CER also makes, what the fuck is this? Tab standard CERR error. It is printing. Consider the following program that doesn't work correctly. Hash include get value int name get value goes to return for क्योंकि इन्होंने function वाला वो ही लगाया. You may need to disable treat warnings as errors for although we expect this program to print, it should print value 1. So it compiled this printing one. Treat warnings. Although we expect this program to print value 4, it should print the value 1. This is an address. What to do if your compiler prints 1 but you wanted to print an address and lessons function pointers. Let's add some debugging statement to these functions. Standard CER get value called CER get value. Okay, these are debugging statements. Wow. Main.cpp. Let's start with this. Standard CER standard console error. Get value called return 4. That's it. Standard C error main function is called main called and then 1. So this get value function is not being called. It can be helpful to not indent them. This makes them easier to find and remove later. If you're using CLang format for a try to indent these lines, you can suppress the automatic formatting like this. Cool. So actually this code shall look like intentionally made a syntax error set numbers set number I in line 12 let this be working. Indicating that where they are called now, see the fundamental value was never called. There must be some problem with the code that calls the function. Let's take a closer look at that. Obviously we have to have opening and closing braces. Remove the temporary debug statements. mkdir fix cp main dot cpp to fix ls cd fix ls then main dot cpp. So I would rather so everything is being commented out. Now let me write this program again. Include our stream int get value is the function declaration, direct implementation of the function. Standard cer get value function called return 4 main function return 0 standard namespace cout get value console error get value, and then we have to apply the fix. Main called everything is all right. Now it shall print C++ main.cpp and main compiled main. Yeah, debugging tactic. You're supposed to add two numbers but doesn't work correctly, so it has to add two numbers. So int x is initialized by get user input enter a number cold return x. Get user input y is initialized by get user input, then add x plus 5. So this might be the problem. 4 plus 5 is 9, but 4 plus 3 is should be 7. So the problem is over here. So the arguments that we are passing to function add should be x and y, but instead it is x and 5. Print result z. Z is the result, and then standard cout. Okay, that's not right. Do you see the error? Even in this, it can be hard to spot. Let's add some code to debug our values. Hmm. Hmm. So where are we adding our values? We are adding standard zero, main x equal to x, y. So we are printing the value of x and y over here using standard namespace and console error line. Equal to 3, variable z. Answer is 9. Variable x and y are getting right value, but variable z isn't. Issue must be between those point which makes function add a key suspect. Let's modify the function. Add x standard c error c. Variable y had value 3 but some function got value 5 with the parameter y. You must have passed the wrong argument. Sure enough, there is it. We passed one more example. Program is very similar to the prior one, but also doesn't work like it should. Main function x is getting initialized, x is y, print result z. It is straightforward. So when get user input is called, cn return minus minus x. What the fuck? This is the problem. This is the problem. Answer is 5. How does that happen? Answer, then add x and y are passed to the add function. X and y, print result z. Result z is an argument for s. Problem is here. You can really see something is going wrong. The user is entering value 4, but main x is the value getting value 3. Let's make sure that the program is getting correct value from the user by adding some debug code. The function get user input. Output should be, you can see the user input is received correctly into user input variable x, and yet somehow main variable x is getting the wrong value. Problem must be between those 2 points. The only culprit left. Get user value, return x. That's odd. When hyphen symbol before x. We haven't covered that yet in these tutorials, so don't worry if you don't know what it means. But even without knowing what it means, through your debugging effort, you can reasonably sure that particular line is fault, thus it's likely that symbol is causing the problem. Here is the output. Why printing statements to debug isn't great? While adding debug statements to the program for diagnostic purposes, common rudimentary technique and functional one, especially when a debugger is not available for some reason. It's not a great for a number of reasons. Debug statements clutter your code. Debug statement clutter the output of the program. Debug statements require modification of your code to both add and to remove, which can introduce new bugs. Debug statements must be removed after that you have done them, which makes them non-reusable. We can do better. We can explore how in future lessons. Is quite heavy. More debugging tactics. We have been sitting for 45 minutes. Contains few debug statements. Int main. And main standard main is called. Get user input. It goes to standard cout. Standard cout, enter the number. X is initialized. Standard in. When X is returned, X is initialized. You entered X. What is then wrong with this program? Because return has not been make them easier is to disable and enable debugging throughout your program is to make the debugging conditional using precursors directive. Comment out to disable be debugging. And if enable debug, and if enable debug, and if enable debug. Now we can enable debugging simply by commenting and commenting define enable debug. This will allow us to use the previously added debug. Just disable this when we are done rather than having to actually remove them from the code. Would go in that, well, that's not included, so we can comment and uncomment as defined in single location. Address this issue with having to remove debug statements and risk in doing so, but at the cost of even more code clutter. Another downside of this approach is to, if you make a typo, example misspelled debug and forget to include header file into the code file, some or all the debugging for that file may not be enabled. So although this is better than unconditional version, there is still room to improve. Using a logger. I'm back. Using a logger, an alternative approach to conditionalized, conditionalized debugging via preprocessor is to send your debugging information to a log. A log is sequential record of event that happened and usually time-stamped. Process of generating log is called logging. Typically, logs are written to a file on disk called a log file. They can be reviewed later. Most applications that can be helped to diagnose the issue for log files. A few advantages: the information returned signature the clutter caused by mingling your normal output and debug output also easily be sent to other people for diagnosis. You can someone using software, you can ask them to send you the log file. It might help give you a clue what the issue is, so it is a very good feature. Standard clog that is intended to be used for writing logging information. However, by default, write to standard error stream. This is same as standard console error. You can rewrite it to a file instead. This one is the area where you generally better off using one of the many existing third-party logging tools available. Which one you use is up to you. For illustrative processes, we'll show what splitting to the logger files look like using plog logger. Plog is implemented as set of header files, so it is easy to include anywhere you need. It's lightweight and easy to use. Include logger headers. Initializing plog defined get user input. Plog D is called defined by plog library. Plog init, plog debug, log file text to initialize the logger. Logger is initialized. Cool. Plog D. Plog is the namespace. Main is called output to the log as if you were writing it to the console. Init standard event. Okay. Main called get user input called. How you include initializing the logger will vary depending on the specific logger you select. Note that conditional compilation directives are also not required using this method, as most loggers have a method to eliminate writing output to the log. This makes code a lot easier to read, as the conditional compilation lines add a lot of clutter. With plog, logging can temporarily be disabled by changing the init statement to the following: plog none. None eliminates the writing of message, essentially turning the logging off. Can we copy it? We copy it. Main.cpp G++ main.cpp. Not include the logger headers. log.h. Yeah, because we don't have it, not machine, and I won't even. If you want to compile the above, use plog in your. You can follow the instructions to install it. cds who is this person? Kiev, Ukraine. He is from Ukraine. And for how long has he been coding? He has been coding since 2013. 2014 he did some contribution. 2015 he did a lot of work. 2016 little bit. 2024 what he was doing. Plog, he did commits and plog. Which company is this? Software engineering services, cybersecurity focused software engineering that delivers Massachusetts. Massachusetts. If it is going to show me a bright screen, then I'm not opening it. As you developer solutions architect, I need this certification. As you developer associate, I need this certification also. Leaf exceptional handling CMake model to with Windows Development Kit kernel unit testing. He's also on LinkedIn. Organizations. Crane software development lead at new system software developer at driver services GUI network multi-threaded application. I also adopt new technology in addition to toggle software and go to the person. I perform code review, improve software development process, help other people to sharp their skills. Programming languages x86 assembly. That is the great thing about our source. SVN installers, Windows, Linux shell, JavaScript, Auto 8, C++11, pretty old version used in Indian college textbook, standard template library, WTL, COM, WDM, file system drivers, NT, API, IPC, RPC, gRPC, multi-threading sockets, remote kernel debugging, crash dump analyzing, reverse engineering, API hooks, object-oriented programming, design patterns, UML, GTest, GMOC, Deoxy, Thrip. I don't know all these RDB add-ins. I know direction, media formation, USB, CMake. I know NetBeans IDE, C-Line. He hasn't first mentioned. 25 co-founder, Kyiv, Ukraine, founder, Kyiv, Ukraine, coordinator, software development lead, senior software developer. He did his masters in computer science before I was born, so he is pretty senior than me. Log portable plog, the one which we were using in our project. Powerful log in less than 1000 lines of code, available on GitHub. Open source project, keyboard layout switcher written in (32) endorsement. We have worked together. Anna, most intelligent and I ever worked as chief. Plog, English, native, quite experienced person. Connect, message, withdraw. Let him accept my, I will tell him how great his plog is. Learn C++.com. Plog repo. Click the green code button and download zip. Finally, for each set the something log include as directory, log will generally be created in same directory. Trip in larger, faster and much feature-rich logger may be preferred, such as SPD log. SPD log has been written by Gabby. Fast logging C++ library. He is from Israel. Smart country. He joined GitHub in 2013 when I was in first class. He joined GitHub. He started making more contributions. Created his first SPD log he created in 2013. 2015 he did 22 commits. Then in 2020 he did a lot more commits. 2026 he has contributed one commit in repository. On what branch has he committed? That's different branch. There are a lot of branches in this repository, fast C++ logging repository. 2025 he did few commits. 2023 he did a lot of commits. Do not use. How many contributions I had? Technical toolkit, Terraform, Prometheus, Ansible, Grafana. In 2025 I had around 298 contributions. I had 22 contributions. I shall get commit -a-m debugging git push -u origin main. Why is it asking me? Keeps on asking me. We will get this problem solved by ChatGPT. No. Store. Now hopefully it shall work. So I will just turn off the screen for a while and then try this command again, because I have to enter my Oh, it did it without my token. Wow. My personal access token for git config. Using integrated debugger. Yeah, G++ has some debugger. I don't. When you run your program, execution begins at the top of the main function, then proceeds sequentially, statement by statement, until the program ends at any point in time while your program is running. Program is keeping track of a lot of things: the value, the variables you are using, which functions have been called, so that when those functions return, the program will know where to go back to, and current point of execution within the program, so it knows which statement to execute next. All this tracked information is called your program state. In previous lessons, we explored various ways to alter your code to help with debugging, including printing diagnostic information or using a logger. These are simple methods for examining the state of the program while it is running. Although these can be effective if used properly, they still have downsides. They require altering your code, which takes time and can introduce new bugs. They clutter your code, making the existing code harder to understand. Behind the techniques we have shown so far is an unstated assumption that once we run the code, it will run to completion, only pausing to accept the input, with no opportunity for us to intervene and inspect the result of the program at whatever point we want. However, what if we were able to remove this assumption? Fortunately, most IDEs come with an integrated tool called debugger to do exactly this. Debugger is a program that allows programmer to control how another program executes, examine the program state while that program is running. For example, the programmer can use debugger to execute a program line by line, examine the value of the variables along the way by comparing the actual value of variables to what is expected and watching the path of execution through the code. Debugger can help immensely in tracking down semantic or logic errors. Power behind debugger is twofold: ability to precisely control execution of the program, ability to view and modify if the desired. Actually, I wrote a question in Discord, so let's see if my question was answered in the Discord or not. Don't CPU fans, don't spin fast. Yeah, somebody actually answered my question. Why you want to learn backend but stay away from development? What in backend is actually is? I don't like web development. I need to learn backend to become a good DevOps engineer. Need to learn. I'm not interested in web development. Need to learn backend to Dheeraj. Who's Dheeraj? Dheeraj is a learner and he is currently doing job. Become a good DevOps engineer. I actually want to understand what's happening inside the tools when we pass commands. Anybody can learn tools, but few understand what's how that tool is functioning. For that, I need one to is functioning inside how APIs are being managed, how things are from inside. Who is Yash? Yash is a contributor. Node. Backend. Usernames have been truncated. What does truncated means? Cool enough, cool enough. I don't care. Boost goals, resume reviews. SDE1, sharing my Qasim Khan's resume. Let's see. And let me just close my Discord. Full stack modern developer with experience. Portfolio plus Node.js, TypeScript, HTML, Tailwind, CSS, AWS, Docker, Nginx, Person, integration, others, or Core CS. Education, MCA from IGNU, CCSU, Russian, Hindi, Urdu. Let it be. Let's focus on the code. Internet, Discord, share it. what tools are you talking about specifically? DevOps tools like Docker, Kubernetes, and CI/CD tools can work with them, but to have better understanding of the infra and whole ecosystem, mastered, backend needs to be mastered, learned. Okay. Folder settings. How can we turn off the notifications? Job switch. Ask for Satya, Sujit, debugging den, pair programming, web app, agentic AI, coding clinic, JavaScript. That needs to be learned for whole ecosystem. If my fan is going to spin fast, then I'm not going to run Discord. What are you trying to gain out of these tool functions? Wait, let me just pause my screen capture. Show. Okay guys, this is where I'm ending my stream.